Chapter 4: Incised Channels, Channel Evolution, and Induced Meandering. The river is the carpenter of its own edifice. Luna Leopold. Introduction. Alluvial stream channels continuously adjust their forms in response to changes in the watershed and to local influences. Significant changes in vegetation, watershed condition, sediment supply, or stream flow patterns can shift the balance of forces that maintain a stable stream morphology. If the impact is drastic, it can initiate a cycle of morphological change to the channel itself through the natural stream channel evolutionary process. Channel incision is one of the common starting points for this process. This chapter addresses some important questions. How can one tell if a channel is incised? How does a channel become incised? Must an incised channel stay incised? What drives the various natural stream channel evolutionary sequences? Can induced meandering influence the evolutionary process? If so, how? Incised channels. An incised channel is one in which a river, stream, or arroyo has lost access to its floodplain. Channel erosion has lowered the bed to the point that only unusually large floods, if any, reach high enough to spread water onto the historic floodplain. Naturally meandering stream channels can become incised if they are directly impaired by roads, railroads, livestock trailing, mining, or other disturbances, and usually become more deeply incised if they are straightened or steepened. Channel incision may be triggered by an increase in the frequency or magnitude of flood events due to deteriorating watershed conditions in headwater areas that may be caused by livestock grazing, fire, road construction, or urbanization. Gullies have many origins. A well-established stable channel, if nicked by a road crossing or livestock trailing, narrowed by floodplain encroachment, or straightened for any reason, may downcut and become a gully as headcutting proceeds upslope with increasing stream velocity. Photo 4-1. Gully erosion may result from the gradual wearing away, abrasion, or deepening of a rill over time, or alternatively, a high-velocity rush of water suddenly eroding soil from a depression or drainage line. Lopez, 2006. Gully formation can often be traced to a change in the watershed, its surface area, relative permeability or roughness. Diversion of surface runoff from an adjacent subwatershed as the result of road construction, land clearing, or leveling will often result in the rapid development or expansion of gullies. Bank height ratio. If channel degradation has lowered the stream bed and the bank is too high above the stream bed to be flooded when the stream just exceeds bankful discharge, the channel is, by definition, incised. The degree of channel incision is measured by the bank height ratio, the ratio of bank height to bank full height. Figure 4-1. For a stream with a healthy floodplain, the ratio is 1, because bank height is equal to bank full height. As degradation lowers the channel bed, the bank height as measured up from the bed increases. Photo 4-2, page 70. According to Rosgin, if this ratio is greater than 1.2, the stream is considered to have a serious incision problem that may not be reversible. This could lead to long-term loss of floodplain access and is an indication of head cutting that may be revealed by a closer look at the longitudinal profile. Abandoned channels. Degraded or channelized streams will often have abandoned channel segments that are no longer hydrologically connected at bank full. This feature can be utilized as a floodplain for an induced meandering project. Alternately, the bed of the stream can be raised to occupy the abandoned channel, restoring the pre-disturbance stream channel and floodplain directly. This type of treatment is called a Rosgin Priority 1 restoration because it is restoration of the original stream in the purest sense. This is the preferred treatment where long segments of the old channel are still intact. For all but the very smallest streams, this will require heavy earth-moving equipment to relocate many cubic yards of earth, to plug the gully and raise the stream high enough for it to flow into the original channel again. Reconnecting an incised stream with its historic channel can repair valuable stream habitat and immediately restore natural function. The gully plug must be designed to resist erosion during the flood of record. Otherwise, the project will catastrophically fail. In many cases, the channel must be dropped back into the gully downstream of the project without creating a head cut. A reach of the dry Cimarron River was restored using this method, photo 4-3. Such work is expensive, highly technical, and beyond the scope of this book. The original cause of degradation must also be addressed if this method, or any other restoration method for that matter, is to succeed. For information on this technique, the authors recommend taking the Natural Channel Design course curriculum taught by Dr. Rosgin, Appendix J, page 219. Hydrology and ecology. If the banks of a stream are at the proper height, they function to hold, carry, and slowly release water stored in the alluvium over time. The horizontal and vertical flow through the alluvium supports streamside vegetation whose roots hold streambank soil in place and provide shade, cover, food, and nesting sites for birds and wildlife. When a channel becomes incised, the water table drops and bank storage decreases. Access to the porous cobble gravel strata is lost, and capillary action that nourishes vegetation ceases because connection with the water table is lost. Riparian vegetation will be eventually replaced by upland species. Since healing an incised channel requires allowing it to increase its width and reestablish or reconnect with a floodplain, it is important to remember that attempting to stop a stream from meandering or stabilizing the stream banks without paying close attention to the evolutionary process will merely postpone evolution toward the stable form. Both banks tend to be periodically scoured in a G or F channel, providing a large supply of sediment during runoff events. Such erosion is commonly viewed as a problem for the watershed and as a source of non-point pollution, turbidity. However, any unguided attempt to repair the bank would likely be counterproductive if the effort hampers the natural evolutionary process, delaying progression towards stability. For example, planting willows on both sides of a straight stream reach or bank armoring, such as riprap or revetments, will inhibit the evolutionary process. Channel evolution and induced meandering. Stream channels are self-maintaining over long periods of time. In many cases, after a disturbance, they will restore themselves to equilibrium, although this will take a period of time longer than the typical attention span, if not lifetime, of a human. Understanding what happens to a stream over its timescale, not ours, is essential to successful stream restoration. When a stream is disturbed from its stable form, it will progress through one of several stream channel evolutionary sequences to achieve equilibrium once again. In 6 of the 9 scenarios illustrated in Figure 4-2, the original stream type is the stable endpoint. Where applicable, induced meandering speeds up the natural process without skipping any steps. The typical geology textbook describes stream channel evolutionary progression as follows. Due to a change in upstream watershed conditions, a previously stable, meandering stream becomes incised, cutting deeper and deeper until it hits bedrock or a new grade control before lateral erosion will have a significant role in producing a wider channel and eventually a new floodplain. Waiting for this to happen naturally is not necessary. Induced meandering can jumpstart the natural meandering process by creating an artificial rock bottom for the stream. Grade control structures to arrest downcutting. This is done in combination with deflectors at proper intervals to direct the power of the stream toward alternate banks. Figure 4-3, page 75. During subsequent flood events, the banks are hydraulically mined by the stream. The increase in sediment supplied by the eroding banks will provide the necessary materials that the stream will sort by size and distribute to the proper locations, building riffles with the largest particles and point bars with finer materials. The point bars will evolve into floodplains adjacent to the channel. This creates the sinuosity and flood-prone width necessary to dissipate stream power and stabilize the system. Induced meandering directly alters the Rosgen channel type by increasing the entrenchment ratio, the width to depth ratio, and sinuosity, while decreasing slope and altering the particle distribution. This is accomplished by arresting downcutting, while fostering terrace erosion that widens the flood-prone area of the stream. Changes in channel morphology occur during floods at or above bank full discharge that have ample power to erode, transport, and redistribute significant amounts of material. Thus, the goal of induced meandering is to halt further downcutting while simultaneously initiating floodplain development. Subsequent channel aggradation may or may not occur within the lifetime of a project. Decreased shear stress on channel bed. A modest increase in sinuosity and channel width achieved by induced meandering can have a profound effect on a stream. Referring to Scenario 9 in Figure 4-2, consider an example from the alteration of a typical drylands gully in which a stable C channel has been mechanically straightened to have a sinuosity of 1.0 and has subsequently incised to become a Rosgen G channel type. Suppose that the valley slope is 2% and the bank full cross-sectional area is 16 feet squared. Suppose further that with the installation of grade control structures and deflectors, the gully has evolved a modest meander pattern with a sinuosity of 1.15, and the width has increased from 11.3 feet to 21 feet. The following example demonstrates what will happen. In the table below, the change in sinuosity has been translated to a change in channel slope, and the change in width has been translated into a change in depth, assuming that the cross-sectional area has not changed much. A equals W times D. Parameter sinuosity before 1.00, after 1.15. Parameter slope before 0.02 feet over feet, after 0.0174 feet over feet. Parameter bankful width before 11.3 feet, after 21.0 feet. Parameter bankful depth before 1.4 feet, after 0.76 feet. These minor changes will bring about a significant change in the critical shear stress, tau c, required to initiate movement of particles. Tau c approximately equal to rho d mean s, in which rho is the density of water, 62.4 pounds over feet to the third power. D mean is the mean depth, and S is the slope. Plugging in the old and new variables into the shear stress equation and then looking in the chart, figure 4-4, page 76, to see the size of particle that will be moved, we get parameter shear stress before 1.76 pounds over feet squared, after 0.825 pounds over feet squared. Parameter particle moved before 228 millimeters, after 123 millimeters. The shear stress has decreased by 53%, and the size of particle that the stream is capable of moving at bankful stage has decreased by 42%. This will cause the larger particles to be deposited on the riffles, slightly raising the grade of the stream within the gully, which will further increase the width to depth ratio. If the trend started by the induced meandering project continues on its own due to vegetation colonizing the point bars, the floodplain will continue to increase in width, eventually changing the stream from a G channel with an entrenchment ratio of less than 1.4 to a C channel with an entrenchment ratio of 2.2 or greater. The damaged channel is now healing and moving toward the stable channel type appropriate to its valley. Figure 4-5, 4-6. Flood events. Using the power of various sized flow events, induced meandering also works at widening the floodplain at a riffle section. Large floods can remove scree at the toe of a terrace, increasing the bottom width of the gully. They can also undercut the toe of a terrace cut bank, where developing pools will wick upward and soak the hard, dry banks, leading to slope failure and collapse, which replaces the scree, thus maintaining a high sediment supply. During a flood event, a riffle will form above a grade control structure. Therefore, placing the weirs just downstream of the widest parts of a gully will cause a riffle to form where it will have the greatest width and the greatest entrenchment ratio. It follows then that moving the location of riffles can directly change the Roskin stream channel type. Very large flood events are powerful enough to erode the toe of the terrace on both sides. As long as grade control structures remain intact and prevent further incision, the floodplain will widen on both sides. This is one way a G, W over D less than 12, can evolve into an F, W over D greater than 12. Extreme floods can have a marked influence on channel evolution in the drylands. In an incised channel, if the bed is not appreciably lowered during an extreme flood, it is likely that both banks will be eroded increasing the W/D ratio significantly in one event. Depending on the site, floods may overtop the terrace and quickly remove the sparse upland vegetation, exposing the alluvium to erosion. Before the flood recedes, strips of the terrace can be planed down to within the flood-prone elevation. It is normal in the drylands for a single, extremely large flood event to increase the flood-prone area and the belt width of an incised stream. This can be a red-letter day for channel evolution. If allowed the chance, subsequent bankful events neatly sculpt a bankful channel and associated floodplains within the newly enlarged flood-prone area. Unfortunately, a typical response to flooding is to allocate emergency funds to bulldoze the entire flood-prone area into a long gravel pit with a U-shaped cross-section, destroying all plants and animals in the process. It would be better to let the water do the work of channel shaping. Low flow periods. Low flow periods are also important in the evolutionary process. They provide an opportunity for maximum growth of riparian vegetation on developing point bars, creating increased plant diversity and the biomass, mass of roots and shoots, necessary to armor the point bar during subsequent storm events. The newly vegetated point bar puts increased stress on the opposite bank, which continues to erode. Water stored in evolving point bars also nourishes the riparian plant community, creating a positive feedback loop. Belt width, a threshold for evolutionary change? Recall from Chapter 2 that the belt width is the width of a corridor that the stream's present meanders would fit within. Figure 4-7. As the meanders extend through lateral erosion of the banks of an incised channel, several key parameters change at the same time. Sinuosity increases and channel slope decreases. As long as the stream is no longer downcutting, erosion of the banks will increase the width of the channel in flood-prone area. All of these variables are incorporated into changes in the belt width. The amount of belt width a stream has in relation to its bankful width may help determine if the stream is close to transitioning to the next step in the channel evolutionary sequence. When the belt width is scaled to the size of the stream, it becomes a fair measure of where an incised stream is within its evolutionary sequence, regardless of the size of the stream. Meander width ratio is this metric. It is an expression of belt width, defined as belt width in feet, divided by bankful width in feet. Figure 4-7. Feet divided by feet has no units, so meander width ratio is a dimensionless measure of a stream's meander pattern, regardless of the size of the stream. To heal an incised channel, it is necessary to increase the meander width ratio until there is enough wiggle room for the development of a floodplain. Measurements on thousands of streams have shown that the average meander width ratio of a Rosgen G channel is 3.7. Figure 4-8. Likewise, on the average, an F stream type has a meander width ratio of 5.3. Perhaps using average values as a restoration target instead of minimum values will help ensure that the transition to the next stream type in the evolutionary sequence is permanent, instead of unstably moving back and forth depending on the nature of annual storms. Note that the minimum meander width ratio for the development of an E-channel type is 20, i.e. the belt width is 20 times as wide as the channel's bankful width. Rosgen, 1996. Figure 4-8, meander width ratio by stream channel type. Data from Rosgen, 1996. Stream type G, minimum 2, average 3.7, maximum 8. Stream type F, minimum 2, average 5.3, maximum 10. Stream type C, minimum 4, average 11.4, maximum 20. Stream type E, minimum 20, average 24.2, maximum 40. Induced meandering. Induced meandering is a marriage of hydrology, geomorphology, and ecology. Induced meandering tweaks the system, speeding up the natural channel evolutionary process. After cross-sectional area, the most predictable parameter of a stream is its bankful width, because the stream has a natural tendency to maintain a constant bankful width appropriate for the watershed area. If the flow becomes partially blocked on one side, then the opposite bank must recede to maintain a constant channel width. Although the stream initially deepens, makes a pool at that site until widening occurs. If impediments are placed at the proper spacing, a new meander pattern can be artificially stimulated in a system that lacks sufficient sinuosity. Photo 4-4. In-stream structures, augmented with the manipulation of stream bank vegetation, will cause the force of running water to expedite channel evolution and floodplain development. The tools of induced meandering are deflectors that direct the erosive power against selected banks and grade control structures that will ensure the erosion will be lateral and not vertical. Photo 4-5. The appropriate design and installation of these structures will accelerate stream channel evolution during subsequent flood events. Structures. Deflectors include vanes and baffles, ideally made from natural materials such as boulders, cobbles, posts, tree trunks, and living plant materials gathered from the vicinity of the restoration site. Deflector effectiveness may be enhanced with the selective planting or removal of stream bank vegetation. Grade control structures include weirs, such as one-rock dams, cobble rundowns, cross vanes, Zuni bowls, and filter dams. Chapter 5. The timing, magnitude, and duration of each flood will cause variable channel response to the installation of in-stream structures. The rate of channel response will depend on the susceptibility of particular stream banks to erosion and on the amount and composition of additional sediment being supplied to the stream for redistribution. The project design must be specifically tailored to the channel being treated so that the dimensions and locations of the structures will cause sufficient erosion of alternate banks to create meanders with the appropriate spacing. The structural integrity of the installed structures must outlast the banks slated for erosion, or they will be removed by the stream before having the desired effect. When in-stream structures are properly designed and built, induced meandering is a feasible and effective method for modifying the dimension, pattern, and profile of incised channels in the Southwest. Rocks alone can be used, but the use of wooden posts or pickets in these structures can improve their effectiveness and reduce maintenance needs. Depending on channel dimension, functional in-stream structures can be economically constructed with hand labor using available local materials. One can change the health of a river single-handedly. Results. Induced meandering will let the water do the work of reforming the shape of the stream, its slope, dimensions, and floodplain. Rates of progress toward meeting management goals will vary due to the natural variability in the timing and magnitude of flood events. Photo 4-6, 4-7, Figure 4-9. Nothing happens without flood events and an adequate supply of sediment. Once induced meandering treatments are in place and the stream begins to approach its dynamically stable condition, a number of self-regulating forces come into play. Over time, increased sinuosity in a building floodplain reduce stream velocity and shear stress. Vegetation growth on the banks is sustained by alluvial storage in the floodplain. The new vegetation regulates erosion and deposition of sediment on the stream banks. Stream structures become incorporated into the stream bank and lose effectiveness. The stream begins to regulate itself in relation to the appropriate channel type for its valley. As it approaches the stable form, it begins to override the induced meandering treatment. Induced meandering is recommended for the treatment of incised channels only, specifically Rosgen channel types G, F, A, and sometimes BC. The purpose of treatment is to nudge the evolutionary process toward a Rosgen C or E type as appropriate to the valley type and bedload characteristics of the stream. Targeting specific eroding banks. When implementing an induced meandering treatment and deciding which bank segments to erode, the effects of expected erosion on stream ecology and morphology must be balanced. Are there places where boulders or lots of large cobble or gravel can be made to fall into the stream, helping to raise its riffles? Will eroding a particular bank increase the sinuosity and better fit an overall meander pattern? Will eroding a high terrace cut bank produce an excess of fine sediment that might impair water quality or have an adverse effect on critical habitat for aquatic organisms? Can the necessary adjustments be accomplished by eroding a low terrace instead? The nature of bank materials is an important consideration. In many deep gullies, sufficient quantities of particles large enough to effectively resist erosion are in short supply. At Cebolla Creek, Cibola County, New Mexico, Albuquerque Wildlife Federation targeted for erosion the only high terrace cut banks where massive boulders and large quantities of cobblestones were poised to fall into the stream channel. During the first runoff season, hand-built baffles directed the flood to undercut these banks, causing large particles to fall into the channel, which stabilized the gully at grade in these places. Subsequent maintenance activities repositioned newly fallen boulders to keep the pressure on the targeted banks. The next runoff event released more large particles that raised the riffles and elegantly stopped a head cut by transforming it into a stable pool while building a new floodplain. Conversely, it is advisable to protect high terrace cut banks if the sediment from their erosion would cause a problem for the ecosystem greater than the benefit to be gained by allowing the terrace to erode. Erosion of high terrace cut banks produces large amounts of sediment per foot of lateral erosion, photo 4-8, page 82. In contrast, eroding a low terrace will produce much less sediment per foot of lateral erosion gained, and low terraces are more easily eroded than high terraces. It is important to weigh the potentially adverse effects of excess sediment production against the benefits derived from an increase in stream length, floodplain width, and vegetative roughness. A project designed by Bill Zeedyke on Nutrioso Creek in southeast Arizona featured habitat for the native Little Colorado River spine dace, Lepidomeda vittata, a federally listed threatened fish species requiring low turbidity. Therefore, second and third terraces were protected from erosion. Channel length was increased using induced meandering, focusing on eroding the first terrace cutbanks only. A significant portion of the sediment coming out of each first terrace cutbank was captured by the next downstream point bar, so that the overall sediment supply of the treated reach was decreased, even as specific banks were intentionally eroded to induce meandering. By targeting specific banks for erosion in an alternating pattern, induced meandering takes some, but not all, of the randomness out of channel adjustment and speeds up the natural evolutionary process. Channel widening from a G to an F is not accomplished uniformly. Typically, an undercut bank may collapse during a flood, dumping a large pile of loose material into the stream. The pile will temporarily divert water away from the eroding bank, increasing stress on the baffle that was built to cause bank erosion. The baffle must persist until the fallen material has washed away, revealing the cut bank again. Perhaps this will not occur until the next flood. Over time, the flood-prone area will widen in steps, and the arroyo will become an F channel that begins to meander, creating a sloping landform which starts to resemble a floodplain. If this lateral erosion continues, the belt width will eventually become wide enough to support a meandering sea channel. Post-flood maintenance and the modification of structure locations and sizing will likely be needed to achieve that goal. Raising the bed. Raising the bed of a creek is fraught with problems. Each weir that raises the bed of the creek creates a drop-off on the downstream side. This could become either a run or a migrating head cut that will erode the bed through the structure. The authors therefore do not recommend raising the bed of the stream reach more than 1 foot in elevation per treatment, and even this small step must be accomplished with sturdily built structures if they are to survive long enough to outlast their purpose. Often, not directly raising the bed of a creek at all, but simply arresting further downcutting while inducing the terraces to erode is the better option. This is all that is required for induced meandering to work. However, there are some cases where the risk of raising the bed is offset by important gains. If the bed of the stream can be raised to allow bankful flows to reconnect with an abandoned floodplain, a G channel can immediately transform back to its previous channel type. If the bed of the stream can be raised to reconnect the water surface at base flow with a cobble layer in the bank, the alluvial recharge capability of the system will increase, increasing base flow and vegetation response. In the case of a G channel with a modest meander pattern, installing weirs on all the riffles will arrest further downcutting, while increasing scour on both banks, increasing the width to depth ratio, and moving the channel toward an F stream type. Each site has unique challenges, and there is no absolute rule to follow. However, weirs will be particularly vulnerable to removal by the stream for the first few floods, or until new riffles have formed above them by the deposition of sediment, which raises the level of the pools above and protects the next upstream weir from erosion. At the downstream end of the project, the bed must be matched with the original channel elevation. Any drop will cause an increase in stream power that must be dissipated safely by installing a sturdily built drop structure such as a crossvein, Zuni bowl, or a constructed riffle. Gullies and small watersheds. A small drainage in a low-energy watershed under 200 acres exhibits two types of sediment transport processes that work somewhat at cross purposes. Hill slope processes work to fill the gully, while large runoff events work to widen and deepen the gully. Hill slope erosional processes contribute sediment to the gully. These processes include dry ravel, freeze-thaw, animal trailing, etc., and cause sediment particles to be released from the banks and transported by the force of gravity towards the gully bottom. Often precipitation events are too small to cause a significant down gully runoff event, but are large enough for tiny rills draining small upland areas to flow down the gully sides, bringing sediment to rest in the gully bottom. Aeolian wind-borne deposits can also help to level out the gully over time. Fine particles come to rest in the wind shadow of the gully, especially if it's covered with vegetation. Large runoff events transport sediment along the gully axis and are responsible for deepening and widening the gully over time. This occurs when the occasional storm is severe enough to produce a significant runoff event, scouring sediment from the channel bottom and sides and transporting this sediment to some point downstream. The balance between these two processes is governed by the pattern of runoff events and the presence or absence of protective vegetation. A high density of grass and multi-stemmed shrubs in the channel bottom will prevent downcutting during a flood event and will assist in trapping material from the eroding banks and uplands. The opposite effect can occur if trees are growing on the banks, but only sparse vegetation is in the channel. The banks are then protected from eroding, while the channel bottom can be easily scoured, causing the gully to become deeper without widening. Accelerated erosion is often caused where an altered landform, such as a poorly drained road, concentrates flow to the natural drainage system. If little vegetation is growing in the gully bottom, the gully system is likely to deepen and lengthen headward, growing new side rills during heavy storms. If a road is properly drained, directing its runoff away from the gullies and harvesting the water within the soil, vegetation will be established in the gully bottoms, and over time, the gullies may begin to heal. Zeedijk, 2006. The gully bottom can be a favorable site for colonization by vegetation because there is more moisture and it is a wind shadow where seeds, leaves, and nutrient material tend to collect between large flood events. Bull, 1977. In some small watersheds, the use of induced meandering may be inappropriate. The return interval for floods powerful enough to erode the banks may be too long to realize improvement during the lifespan of the project. Floods depend on watershed size, precipitation amounts, soil texture, and bank erodibility. Unless treatment will drive the system towards a natural state appropriate for the landform, it is not restoration. A more appropriate approach might be to correct anthropogenic drainage problems that cause concentrated runoff, and then plant many shrubs or a lush grass all along the gully bottom. A series of one-rock dams or cobble channel liners, Chapter 5, could stabilize gully bottom soils long enough to trigger colonization by native vegetation. Photos 4-9, 4-10. As soon as sufficient vegetation is established, the energy balance shifts and the gully gradually widens and becomes shallower. Summary. An incised channel is a channel that has lost access to its floodplain. Once incised, a channel will tend to evolve through a series of stages, channel types, that will eventually return it to the pre-disturbance condition or type characteristic of its valley type. This tendency is the core principle upon which the induced meandering concept is based. Since the natural process of channel evolution may take a lifetime or more, the goal of induced meandering is to speed up the evolutionary process by halting channel downcutting and initiating floodplain development. This is accomplished by redirecting the energy of floodwater away from the bed and into the banks instead. By reading the landscape, fluvial geomorphologists can tell a channel's recent evolution. The Rosgen stream channel evolutionary sequences provide a scientific basis for the induced meandering method. By understanding the evolutionary process and recognizing where a stream is in that process, a riparian restorationist can help the land manager make better decisions. For example, efforts to stabilize an eroding bank of an incised channel may be defeating if the stream would then be unable to create, through lateral erosion, sufficient space to accommodate a meandering channel. Similarly, it would be inappropriate to modify a dynamically stable channel by attempting to increase its width, flatten its slope, or increase its sinuosity, because such alterations would cause the channel to over-widen and interfere with the ability of the stream to accommodate flood flows or transport its bed load.